of F delta to delta, working in one kind of coordination, and this is the form that will come out when the bracket is sloped at all. If you this bracket, Hamiltonian will be if we type Hamiltonian, this will come out, and over here will be times and 1 over ns, and then this can be this is the simplest form that we'll get in the brackets formula solving. And if we get the bracket of this, and this one, actually we can solve this in a faster way using this equation that I made. This is the equation that I made, and this tells the exchanging value of delta t and location n. If we put it in the formula, then the thing that will come out is and t2 go. We'll put it like this, and this one will be as, because we timed it, and then exchanging value of the t and location, and this one to 1 over ns, and this will be e and for 1 2 n. This is the simplest we can get. And also so this is telling the spin of a magnetism. So the spin of the magnetism, since it is this, there is over this will be as delta x, and this will be as pi a, b, and p. Now this one is the bracket notation. Bracket notation going from this side. So, right, and since it has this, we'll put location mu squared dd times v, and this will be inside the matrix mechanics. Now another form of the matrix mechanics, the energy flowing in a direction of the matrix, which was first proposed by Wolfgang Pauli, who was my background picture, in 1928, I guess. He said that when R going to the radius side and T is exchanged, not with the separation of a comma, and on times of a wave function, then the energy floating to the location mu square will become, going to the opposite side of the radii, will become the bracket notation, and the mu square will, can also be represented as the dd times d, and over mu, which is root dd times d, and the bracket notation right here, and the location underneath. That is why I have talked about the bracket notation. This can be in other forms as dd times d inside the bracket, and the psi of n when n is photon. The next form will be, the more simplified one will be in a fraction. N is axion. By this form, the bracket notation will be in the same side now, which is equal to the big value of, we put T1 as a spatial value and T2 as a spatial value to go into theta. There will be phi. There is no value inside the equation, and in there will there will go into the radius opposite, and go into the radius side and the opposite of the radius side. Now, as this form goes on, we'll have another graph that will look like this, and have this as dd times d, as mu squared. But then d times d and the mu squared equals to d times d equals to 0. It's comparably the same thing. So when mu squared is a axiom and the n is a photon, the bracket notation is different, like this. The bracket notation will be like of xi of this side going and this side going, like this. And the bracket notation will happen with the xi root d times d and the bracket notation, the dx, and here mu squared, so d times d mu squared. And see, about here, the bracket notation may be in the form that might disappear, but in this form is represented when n is a photon, and this form is represented when n is an axiom, right? And when n is the axiom, then 1 over ns will be inside the bracket notation of the side, right? So inside the matrix will be in another form. There will be another flow going on like this, and this one will be dd times d. But then there will be another flow, and I'll explain like that. See, this one that I first was f to delta was actually in the direction of r going to the side of the radius, and then there was phi, which is 0 of inside the bracket notation. And when we extend this, there will be this value. Can you guess what this value is? The value, yes, the value is inside this. This value is I e minus 1 comma I h dash dash. Like this. And this is a photon and this is an axiom. This is a very important general duality formation, and this is the basic equation for the general duality, and this is when n is axiom inside the general duality. Bracket notation, when it's 0, expressed as a phi inside here, which leads to another of the new bracket notation, bracket notation, same as this one. E minus will be an electron going past like this, and the IH is the imaginary number and the Hamiltonian. When put the xi exchanging value with the Hamiltonian xi and the bracket notation going to the same set with a phi in the middle. This will be since this is inside the F to delta, the electron goes on under, over through this. And this is all happening inside because of the F to delta. Now, what if actually this became like this? What if it was this? F delta to delta, but then it doesn't match the bracket notation. Then the electron of this electron will go on like this bracket notation value went on the electron going like this through the flow. This electron going on will go like this underneath the flow. Then how should we make it over the flow? To make it over the flow, most people think that we should do something like F to delta, exchanging values to delta, and delta 2, and put this as 1 and phi without that. Most people think like that, but the thing is that over the flow was delta x, pi a, b, and p, d times d. So this does not fit. What will happen in this will go up above here, but we want just right over the flow, because when we put it here, when we put the electron here, E minus here, then the electron will automatically go down and match the flow of over, because the electron is attached to the flow. But then if the electron is here, it will take infinity time for the electron to go down the flow if it is here. But then this is telling that the electron is like here. So what we actually should write is this. What we actually should write is dx to pi a b p 2 d e. This should be actually the correct graph. And with this phi, which is 0. Now 0, right? But then the 0, does it represent something? And yes, it does. It represents this, which was 0. So in another form, it will be written like this: dx to a b p 2 d times d, and now we will see something right here. Now mu square equals d e times. You see here, there is a d times d right here. And there is the dt times d right here in the same spot. So what we can promote this is, we can actually promote this to phi and the phi inside the calculus times d1 times d2 and ab times dx. This one. This actually, we can actually estimate just right away to this, but then it'll be very hard to calculate because we can't see the similarity if we don't have this. That's why I've done this. But then the problem is, if it's this, won't it be like here? So what we do is we square it in mu times. Then we'll have all three flows, right? The first flow will be this F delta to delta. First flow going under, second flow F delta dot. Third flow, this flow is kind of weird. Phi and calculus, not F. Calculus with the phi inside and the ABP times dx dd times d1 dd times d2 three flows are here, and I wanted to talk about this until now. This flow will be like this underneath. This flow will be like this through. This flow will be like this over. Done.